The fundamental theorem of arithmetic, Theorem 1.1. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to reflect on what we've already covered. In our previous lesson, we practiced the practical side of number theory, specifically, how to break down a composite number into its prime factors using visual methods like the factor tree. You've already seen how a large number can be split into smaller and smaller pieces until only primes are left. Now, we are going to step up from just doing the process to understanding the logic behind it. We are moving from the method to the underlying mathematical law that governs this entire process. This isn't just any rule. It is a principle so foundational to the entire field of mathematics that it is known as the fundamental theorem of arithmetic. Over the next few slides, we will look at exactly what this theorem states and why it is considered the backbone of number theory. 1. The formal statement. Now that we've introduced the name of this theorem, let's look at the formal statement itself. If you were to read it from a textbook, it would say, every composite number can be expressed or factorized as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. I know that sounds like a lot of mathematical jargon, so let's slow down and break this definition into 3 key components to really grasp what it's telling us. First, we have the composite number. As we touched on in our previous lesson, this is simply any positive integer greater than one that isn't prime. In other words, it's a number that has more than just 2 factors. Second, we have the product of primes. This part is telling us that any composite number can be written as a multiplication of prime numbers. You know, those building blocks like 2, 3, 5, 7, 11, and so on. Finally, and most importantly, we have uniqueness. This is the heart of the theorem and the most critical part to understand. Uniqueness means there is only one single, specific set of prime numbers that, when multiplied together, will result in that specific composite number. No other combination of primes exists that can produce that same result. As we will see in the next few slides, this uniqueness is what ensures that no matter which path you take to factorize a number, you will always arrive at the exact same destination. 2. Historical context. Now that we have defined what this theorem actually says, you might be wondering where this idea came from. It isn't just a modern invention. The roots of this theorem actually go back all the way to ancient Greece. The concept was first discussed in a very famous work called Euclid's Elements. If you ever study the history of mathematics, you'll find that this is one of the most influential mathematical texts in human history. However, there is an important distinction to make here. While Euclid provided the essential groundwork and the initial logic, he didn't provide the full, rigorous proof we use today. That complete, formal proof was provided much later by the legendary German mathematician, Carl Friedrich Gauss. This brings us to why we use such a heavy title for this concept. Because this theorem plays such a central, foundational role in the field of number theory, we refer to it as the fundamental theorem of arithmetic. It truly is the bedrock upon which much of modern mathematics is built. Now, let's look at a practical example to see this uniqueness in action. 3. Understanding uniqueness with an example. Now that we have seen the formal definition and the history behind this theorem, you might be asking yourself a very practical question. If I start factorizing a number differently than my classmate, will we end up with different results? Well, the answer is a definitive no. As we discussed in the previous slide regarding uniqueness, the path you take through the factor tree may differ, but the final destination, the set of prime factors, will always be identical. Let's look at a concrete example to prove this. We are going to factorize the number 120. First, let's look at method A, where we start by dividing by the smallest prime, which is 2. In step 1, 120 equals 2 times 60. In step 2, we break down 60 into 2 times 30. In step text $3, we break 30 down into 2 times 15. Finally, in step 4, we break 15 into 3 times 5. so our final string of factors is 2, 2, 2, 3, and 5. Now let's try method B, where we take a completely different starting point, perhaps by using 10 and 12. In step 1, 120 equals 10 times 12. In step 2, we break those down into 2 times 5 and 2 times 6. In step 3, we break that 6 down into 2 times 3. If we look at all our pieces, we have 2, 5, 2, 2, and 3. If we rearrange the order of these factors, as I mentioned in the definition, we get exactly the same result: 2, 2, 2, 3, and 5. The key observation here is that regardless of the method used, the prime factors are always 3 2s, 1 3, and 1 5. To make this even cleaner, we can write this using exponents, which gives us 120 equals 2 to the power of 3 times 3 to the power of 1 times 5 to the power of 1. This perfectly illustrates the uniqueness we talked about earlier. To help you visualize why this is so consistent, let's move on to a helpful analogy involving chemistry. 4. Real-world analogy: the chemical formula of numbers. Now, I know that the idea of uniqueness in mathematics can sometimes feel a bit abstract. So, to help you visualize this concept, let's step away from numbers for a moment and think about chemistry. Imagine that prime numbers are like the basic chemical elements. You know, things like hydrogen, oxygen, and carbon. In this analogy, composite numbers are like molecules, such as water or glucose. Think about a water molecule, which we write as H2O to be specifically water. That molecule must consist of exactly 2 hydrogen atoms and 1 oxygen atom. If you change the count, it's no longer water. The fundamental theorem of arithmetic works exactly the same way. Take the number 12, for example. Its chemical formula must consist of exactly 2 2s and 1 3, which we write as 2 times 2 times 3. Just as you saw in our previous example with the number 120, the ingredients are fixed. If you change the elements, meaning you change the prime factors, you inevitably change the molecule or the resulting composite number. This is why we say the factorization is unique. The recipe never changes. 5. Common mistakes to avoid. First, let's talk about ignoring the order clause. As we saw in our example with the number 120 earlier, you might write your factors as 2 times 3 times 5, while a classmate might write 5 times 2 times 3. It is very important to remember that these are not different factorizations. The theorem explicitly states that the factorization is unique, apart from the order. As long as the set of prime numbers is the same, the order in which you list them does not matter. Second, watch out for including non-primes in your final answer. A very common error is stopping the factorization process too early. For instance, if you write 60 equals 2 times 2 times 15, you haven't actually finished the job. Why? Because 15 is still a composite number. To satisfy the theorem, you must continue breaking it down until every single factor is prime. So, the correct, complete version would 60 equals 2 times 2 times 3 times 5. Finally, be careful not to confuse prime and composite numbers. Remember, the entire purpose of this theorem is to describe how composite numbers are built. Prime numbers are already in their simplest, most fundamental form. They don't need to be factorized because they cannot be broken down any further. Now, before we wrap up our lesson and look at the final summary, I want to pause and discuss some common pitfalls. Even though the fundamental theorem of arithmetic seems straightforward, there are 3 specific mistakes I often see students make during exams. Keep these 3 points in mind, and you will have a much stronger grasp of this theorem as we move into our final takeaways. Key takeaways. First, let's revisit the core idea. Think back to our analogy of chemical molecules. Just as we discussed, every composite number is built from a unique recipe of prime numbers. These primes are the essential building blocks that make up the number. To put this into a formal mathematical notation, the theorem tells us that any composite number is equal to p sub 1, multiplied by p sub 2, and so on, up to p sub n, where each of these p's represents a prime factor. It is essentially a mathematical way of writing out that recipe. The most vital takeaway, however, is the concept of uniqueness. As we saw in our example with the number 120, even if you and a classmate use different paths or different starting points in your factor trees, you will always arrive at the exact same destination. The set of prime factors will be identical every single time, regardless of the order. Finally, just as a bit of historical context to remember, keep in mind that while the foundations of this idea were laid down by the ancient Greek mathematician Euclid, it was the great German mathematician Carl Friedrich Gauss who later provided the rigorous formal proof we rely on today. All right, we have reached the end of our lesson, so let's take a moment to recap everything we have covered today to ensure the fundamental theorem of arithmetic is crystal clear. Now, as long as you remember that every number has its own unique prime signature, you have mastered the heart of this theorem. Well done.